Hi everyone! Today I would like to show you a paper by Nader Bshouty called Almost Optimal Distribution Free Junta Testing. Okay, so what am I going to talk about today? First of all, I'll give you a short introduction and a description of the problem that we are talking about. I will show you some previous work and results. I will show you the main algorithm of the paper, then explain the algorithm without any proofs, and then I will prove the algorithm for the K-Junta input. After that, same thing for the epsilon far functions, okay, Junta. I'll calculate the complexity of the queries, and then I'll show you some open problems that we don't have an answer for today. Okay, so let's start with the classic model. We have an oracle that accesses a function which receives a Boolean vector with the length n and outputs f of x, which is a binary string that the oracle received. A Boolean vector with the length n means a number which consists of n digits where the digits could be 0 or 1. For example, this Boolean vector here has the length of 6. On the function, there is a distribution, which is an oracle that draws a random Boolean vector according to the distribution D with the length n. In this paper, the distribution D will be uniform distribution. So if we decide to press the button, the oracle will randomly, according to the distribution D, generate a Boolean vector x with the length n, and the function will output the function on vector x result. Here we have a second option over here. In this option, we can manually insert a vector x and get the function on vector x result. In this option, we do not use the oracle to randomly generate, according to the distribution D, a Boolean vector x with the length n, but we choose that vector with the length n. In both options and cases, the function f is unknown. Now I'll show you a similar model named K-Junta. In this model, the function isn't any function. The function is affected by at most k variables. K needs to be a known number. In this example here, we can see that the function is defined by 5 variables. X is 1, 4, 5. But the function's output relies only on 4 variables, x1, x2, x3, and x4. So this function is a for Junta. The function and its variables are unknown, and the x variable are called relevant variables. In this work, we want to build an algorithm that receives this type of box with 2 methods. One is to press the button, and the other one is inserting manually the vector, like I have explained before. We want to receive a parameter k and a distance parameter epsilon. The expected output should return except, with a probability of at least 2/3 if the function is K-Junta. This case is called a two-sided case. If the probability would be 1 instead of 2/3, then it would be a one-sided case. If f is epsilon far from any K-Junta, then we should expect the output to be rejected with a probability of at least 2/3. We say that f is epsilon far from every K-Junta with respect to D if for every K-Junta, G and F is epsilon far from G with respect to D. We will use U to denote the uniform distribution over all the Boolean vectors with the length n. F and g both are functions that receive n Boolean variables and outputs a 0 or a 1, and a probability distribution d over all the Boolean vectors with the length n. Okay, so what does this actually mean? Let's say our world here consists of all the k Junta functions. So if we take a k Junta function, it would be epsilon far if and only if it satisfies this expression over here. The probability when generating a vector with distribution d is a uniform distribution, that f would be different from g is equal or greater than epsilon. Here I will define for this algorithm, which is a distribution-free testing algorithm, the query complexity of the algorithm is the number of queries made on f. And of course our motivation is that this number would be as small as possible. Okay, before we dive in, I want to go over some notations so things will be easier for me to explain. Alright, so this notation n over here means a group of n numbers from 1 until n. Alright, and for x in n, and x is a vector with the length n, we write x, capital X, belongs to 0, 1 powered by x, to denote the projection of x over coordinates in capital X. For example, if we take a look over here, then x subscript capital X, right? So x capital X, we mean x subscript capital X, will be the projection over x coordinates in capital X, which will be this vector. Okay, as we see, our capital X is 2, 4, and 6, and our x is x's 1 through 7. And if we project x on capital X, we will take the 2nd, the 4th, and the 6th position in the indices of x, and this would be our vector. Okay, so by WHP we mean with high probability, and by WLOG we mean without the loss of generality. Okay, for x1, x2 in n, where x1 cap x2 is the empty set, which means they don't have any shared elements, and x belongs to 0, 1 powered by x1, and y belongs to 0, 1 powered by x2, we write x concatenation to denote their concatenation, the string in 0, 1, x1 union x2 that agrees with x over coordinates in x1 and agrees with y over x2. For two vectors, xy belongs to the vectors with length n, denote the operator circle as this example over here. So we have x which are zeros, so this vector is just 4 zeros, and we have this vector over here y which is just 1s, 4, 1. And if we take x 1, 4, then we go for the first index of x and the fourth index of x, and we write them down, 0 and 0. For y, if we take the second and the third index, then we get 1 and 1. So the concatenation between x14 and y23 would be the same as x14 and the concatenation between y14 bar, which is basically the completion of 1,4. So if we take the fourth index, they are basically with the 2 and the 3, they complete each other to be the full vector 1. And this would be equal 0, 1, 1, 0, because we take the first index to be this 0 of x. The second index is y, and then the third also y, and the fourth is from x. So this is what we get. Okay. So what kind of work and results do we know already today? Let's say, for example, that our distribution is uniform. If we want to look at the upper bounds of the number of queries, we have two cases, adaptive and non-adaptive. For the K-Junta problem, the adaptive algorithm uses bounded numbers of steps in each phase of the algorithm, while the non-adaptive version, the oracle will randomly, according to the distribution D, generate a Boolean vector x with the length n, and then the algorithm applies tests on it dynamically until finding a solution, without bounding the number of steps in advance. We can see that the discoveries of the numbers of queries for the lower bounds are more recent. We can see that the non-adaptive cases, the bounds are firmly tight, and in the adaptive cases, the bounds are tight up to a certain k divided by epsilon. Okay. If you want to talk about one-sided upper bounds, these are the results we will get. So for the non-adaptive case, we get O of 2 powered by k divided by epsilon query. And the adaptive case, we get O of k squared divided by epsilon queries. In the one-sided lower bounds, for the non-adaptive case, we get omega of 2 powered by k divided by 3, or that divided by epsilon queries. And for the adaptive case, omega of k log k queries. Okay, here we have the two-sided lower bounds, which is already known by Seglam over here, which is omega of k log k. But the main conclusion of this paper is by Bshouty is the two-sided upper bound for the adaptive case, in which we will show and explain the algorithm with a complexity of k log k. Another conclusion is that the upper bound, in contrast to the lower bounds, is a tight bound. Okay. So let's go over some definitions from previous results so we can understand this paper. So for a Boolean function f and x, which belongs to a part of n, we say that capital X is a relevant set of f if there are a, b, which are vectors with the length n, a Boolean vector with the length n, such that f of a is not equal to f of bx, b subscript capital X, concatenation a subscript capital X bar. So capital X bar is basically n, but without x, without capital X. When capital X equals I, then we say that xi is a relevant variable of f. If capital X is a relevant set of f, then x of capital X contains at least one relevant variable of f. Okay, let's go over the next 4 lemmas that were used in previous works and will be useful for us here. So, lemma 2. If a capital Xi, where I belongs to R, is a partition of n, then for any Boolean function f, the number of relevant sets, capital Xi of f, is at most the number of relevant variables of f. Lemma 3. Let capital Xi, when I belongs to R, be a partition of n. Let f be a Boolean function and u is a Boolean vector with the length n. If f of u is not equal to f of 0, then a relevant set, capital XL, of f with a string where v is also a vector, a Boolean vector with the length n, that satisfies f of v not equal to f of 0 subscript capital X L concatenation v subscript capital X L bar can be found with log2 R query, and you see it's rounded up. This was found by Chen et al. Len 4. There exists a one-sided adaptive algorithm, uniform Junta, of f, k, epsilon, and delta, reject with a probability at least 1 minus delta when it is epsilon far from every k Junta, which is O of k divided by epsilon plus k log k log 1 divided by delta queries. Lemma 5. Let D be any probability distribution over the Boolean vectors with the length n. If f is epsilon far from every k Junta with respect to D, then for any j which subsets n, j, the size of j, is equal or less is equal or less to k. We have the probability where both x and y belongs to the distribution x distribution D and y is uniform. The probability of f of x not equal f of x subscript j concatenation y subscript j bar is greater or equal to epsilon. Okay, so let's prove lemma 5. Let j subsets n of size, the size of j, is smaller or equal to k. For every fixed y, which is a Boolean vector with the length n, the function f of x subscript j concatenation y subscript j bar is k Junta, and therefore the probability where x belongs to D, f of x is not equal f of x concatenation j, x subscript j concatenation y subscript j bar is greater or equal to epsilon. Therefore, the probability of f of x not equaling f of x subscript j concatenation y subscript j bar is greater or equal to epsilon. Okay, so this is the scheme of the algorithm, and as you can see, we have two paths. The green path, which represents the path we will take with our input function k Junta, and the blue path over here in the left, which represents the path we will take if the input function is epsilon far from every k Junta. In this paper, we will split the algorithm into 4 parts, which are the purple rectangles. over here. So basically, what we want is for the algorithm to output reject if f is epsilon far from k junta, and output accept if f is k junta. What we have here in the red bubbles are when the algorithm fails to identify the function correctly as a k junta and marks the function as not k junta. Over here. Later on, I will show you and explain that if f is k junta, we are going to go through with a probability of 2/3, of at least 2/3, and to reach the end, and the verdict of the algorithm will be that f really is a k junta. Okay, let's talk about the first part of the algorithm. In the first part, we will see the initialization and a few tests. Okay, the first part of the algorithm is the initialization, where the algorithm gets a parameter k over here, a function f and distribution d over here, and epsilon, of course. First of all, the algorithm divides the grouping of numbers into sets in a uniform way. So over here, we choose uniform at a random partition. The group x1 and xr are the division of n into partitions. Okay, so we also need to remember that we are setting r to be 2k squared. Okay, so what happens after the algorithm divides the number into sets? Let's say this is our set of numbers over here, and this set represents the indices of our variables. Okay? And without the loss of generality, this is how it was divided, like this. Like x1, 1, 2, 2, 3, you get the deal. After we receive a function, then the corresponding variables that aren't relevant will be dropped. x1 through xr is the division of the indices of the variables on top of which the function f is defined, while x of capital X index I equals to all variables x subscript j, such that the index j belongs to the set of indices xi. So we got fact 1. If f is k junta, then with high probability each set of variables x of xi is equal to xj, such that j is equal to xi, capital Xi, contains at most one relevant variable. Okay. Next to the second part. In the second part, we want to find all the relevant sets. Here we have a set of capital X, whose purpose is to find all the relevant sets. Okay. In the end of this part, we will have a union of all the relevant sets. Capital I will have all the indices of the relevant sets, and T of X is a counter which we address later on. Here in line 4, over here, we enter a loop and repeat it nth number of times, where m is equal to ln of 2k, 15k, divided by epsilon. Okay, so inside the loop in line 5, we choose a vector with the distribution d. In line 6, we increase the counter by 1. and perform this test over here in line 7. In this test, we are trying to check if there are more relevant sets which we haven't found yet. In line 8, we search and find the relevant sets. This is how we find it. We activate the function f on ux concatenation 0 capital X bar. U subscript capital X concatenation 0 subscript capital X bar. So we check that if it's not equal to f. If without the loss of generality, the result of the function shouldn't be different in this section, but it could be different in this section over here. If there's a difference, then there is a relevant variable that causes this inequality over here in line 7. If there is always inequality, then this means there are no longer any relevant sets and we can continue to the next stage. But if there is an inequality, we go over to line 8 through 9 to find the relevant set using binary search and find a vector by using the inequality in line 9. Let's say without the loss of generality that the relevant set is x capital X subscript L. Here. With the first indices, the inequality checks if the function on vector v is different from the function on the vector where we change the two relevant indices to 0. We will call this vector the indicative vector, as this vector indicates that our set is a relevant set. And if there really is an inequality, then that means we have a relevant variable in this section over here. In line 8, we also update the set capital I. Okay. And in line 10, if we found more than k relevant variables, then the function is not k-junta and we output reject. If not, then in line 11, we reduce the counter back to 0. Okay. So when we say that the Boolean function f from all the Boolean vectors with length n to 0 or 1 is a literal if f belongs to x's 1 through n and x's 1 through n bar. In steps 3 through 12, the algorithm finds a set of relevant sets, capital Xi, where I belongs to capital I, where capital I is a subset of 1 through R. And fact number 2, relevant sets, capital Xi, where I belongs to capital I, such that for capital X equals the union where I belongs to capital I of capital X subscript. With high probability, the function f of x subscript capital X concatenation 0 subscript capital X bar is epsilon divided by 2 close to f with respect to d. Fact number 3. If f is epsilon far from every k-junta with respect to d, then with high probability that the function of the function f on x subscript capital X concatenation 0 subscript capital X bar is half epsilon far for every k-junta with respect to d. Fact number 4. With high probability for each L in capital I, there is tau of L in capital XL such that f of x subscript capital XL concatenation V powered by L V subscript capital XL powered by L is close to some literal in x tau L and x tau L bar. With respect to the uniform distribution, of course. Okay. In the next stage of the algorithm, we will use this algorithm here with k equal 1 to check if our function behaves like a one junta in each individual relevant section. Now we want to go over and check how our function behaves in each relevant set. We want it to be close to a literal, meaning being dependent only on one variable. In line 13, we go over all the relevant variables of the relevant sets. And in line 14, we activate the function on x subscript capital X L concatenation V subscript capital XL bar powered by L. Okay, so all this we use as an input for the uniform junta function to check if the function behaves like one junta. If it does, we will see later that the output will always be accept. Otherwise, if the function is 1 divided by 30 far from every one junta, then with high probability of 14 divided by 15, the output will be rejected with a probability of 1 divided by 50. We'll get a mistake in the output. If f is one junta, it doesn't mean yet that the function is a literal, because it could also be a constant. So in line 17, we check if f is a constant or not. In line 16, we choose uniformly a vector b. In line 17, we project it on the relevant section and check if there is a difference if we change the bits in the relevant section. If there is no difference, then f is a constant and vice versa. If the function is a constant, then we also output reject. Okay. So, if f is k-junta by facts 1 and 2, it passes this test with a certain probability. If it rejects, then f is not k-junta with a certain probability. If it passes the test, then we still don't know for sure if f is not k-junta. That we will calculate soon. Alright. Before we go over to the last test, we should note that if f is k-junta, then f of x subscript every relevant set is the same as f on x subscript all the indices of all the relevant variables. In this last step, we basically want to test how far is f on x subscript capital X The problem is that we don't know exactly who J is, so the test is difficult to perform. Okay, so since J is unknown, we can do this trick over here. First we choose Z uniformly and then switch Z's indices with 0 in the relevant indices. And then check if this f is different from f where we change the elements except the places over here. If f is k-junta, then there should be equality, because if we change the values in the irrelevant areas, then it shouldn't make a difference. If there is an inequality, then soon we will see that with a probability that f is epsilon divided by 2 far from every k-junta. Okay. So this is the last section of the algorithm. And here we have two loops. An external loop in line 18, which is repeated mtag number of times. Mtag is equal to this number over here, 2 ln 15 divided by epsilon. We will get this number later on. Inside all of this section, we want to build this vector z in the same way I explained earlier, uniformly. But after building it uniformly, switch the relevant sections with 0. In line 20, we go over every relevant set, and for every relevant set, we define two sets in line 21. Set y L0 and set y L1. YL0 will be all the indices where W is 0, and YL1 will be all the indices where W is 1. In line 22, we find two counters, GL0 and GL1, which we will soon get to. In line 23, we get to the second loop, inside the inside loop, which repeat h number of times, and h equals to ln of 15 mtag k divided by ln of 4 divided by 3. I will explain this number as well in another slide. Okay. In line 24, we choose again a vector uniformly and perform the following tests. In the first test, we take the projection of B on the zeros section in relation to W and see if there's a difference there. If there is a difference, then the relevant variable is somewhere in that zeros section. And we increase the zeros counter GL0 by 1 over here. The second test is the same thing, but this time we change the ones section and increase GL1 by 1. What we expect is an increase in only one of the counters, GL1 or GL0. So in line 25, we expect to get either GL0 equals to 0 and GL1 equals to h, or the other way around, GL0 equal to h and GL1 equals to 0. Okay. In line 26, without the loss of generality, if it turned out that GL0 is equal to h, then the relevant variable is in the zeros section. Z was chosen uniformly, but because we know that the relevant variable is in the zeros section, we will change Z so that the relevant bits of Z will be 0. In line 28, if F is k-junta, there will be an inequality and the output will be accept. Otherwise, with high probability, we assume that F isn't k-junta. Okay, let's go over the scheme one more time. In the first part, we have a function as input. It could be either k-junta or epsilon far from k-junta. In this part, we divide into sets. Okay. In the second part, we look for the relevant sets. In the third part, we perform tests on every set. And in the forward final part, we perform a final test to see if f is k-junta or not with high probability. Let's go over the algorithm again in the path where f is k-junta. Okay. So here in the first part, we make the partitions and we stay with the same k-junta function. And we have lemma 6. Consider steps 1 through 2 in the algorithm. If f is k-junta, then with high probability at least 2/3 for each I in R, the set x of capital Xi is equal to xj, where j is in capital Xi, contains at most one relevant variable of f. Alright, so let's prove lemma 6. Let xi1 and xi2 be two relevant variables in f. The probability that xi1 and xi2 are in the same set is 1 divided by r. By the union bound, it follows that the probability that some relevant variables xi1 and xi2 in f are in the same set is at most k choose 2 divided by r, which is equal to k times k minus 1 divided by 2r. And if we remember correctly, in the first step, in step number 1, we said that r is equal to k squared. So we can do this. And now this is equal to k times k minus 1 divided by 4k squared, which is equal to 1/4 minus 1 divided by 4k. And this is less or equal to 1/3. Okay, so let's continue to the second part. In this part, we can assume that our partition is good with high probability of 2/3, and every set will contain one relevant variable at most. This time f is k-junta. Then if f is k-junta, then we will pass this test, and f on x subscript capital X will also be k-junta. Okay. So going into the third part now, we will also pass these two tests over here. In line 14, we'll get accept, and in line 17, we'll get accept because of how the function reacts. Alright, so we have lemma 7. If f is k-junta and each x of capital Xi contains at most one relevant variable of f, then each x of capital Xi, where I is in capital I, contains exactly one relevant variable. The algorithm reaches step 18. Okay, so let's prove lemma 7. Proof. By lemma 3 in steps 7 through 9 for L in capital I, f of v powered by L is not equal to f of 0 subscript capital XL concatenation v subscript capital XL bar powered by L. And therefore, x of capital XL contains exactly one relevant variable. For example, we have over here v powered by L. This thing here means basically the size of capital XL, just for this example, so we can understand. So we can see that v0 for v subscript capital XL minus 1 followed by L, like all the indices over here, they are not equal to the zeros over here. So this vector is not equal to this vector, which is 0 subscript capital XL concatenation V subscript capital XL bar powered by L. Okay, so first, for every L in I, f of x subscript capital L concatenation V subscript capital XL bar powered by L is a literal. If the algorithm does not reach step 18, then it either halts in step 10, 15, or 17. If it halts in step 10, then capital I is greater than k, and therefore by lemma 2 f contains more than k relevant variables, and then it is not k junta. Okay. If it holds in step 15, then by lemma 4, for some capital XL, where L belongs to capital I, f of x subscript capital XL concatenation V subscript capital XL bar powered by L is not one junta, literal or constant function, and therefore capital XL contains at least 2 relevant variables. If it holds in step 17, then basically f of B subscript capital XL concatenation V subscript capital XL bar powered by L is equal to f of B subscript capital XL bar concatenation V subscript capital XL bar powered by L, and then this function over here is not a literal. In all cases, we get a contradiction. Let's continue to the last part. In here we build Z, like I explained before, and perform the tests that should lead us to output except at a probability of 1 because of the next line. Okay. Alright, so lemma 8. If f is k junta and every capital Xi, where I is between 1 and r, contains at most one relevant index of f, then the algorithm output will be except. Alright, let's prove lemma number 8. By lemma 7, the algorithm reaches step 18. We now show that it reaches step 29. So now we need to show that the algorithm does not halt in step 25 or 28, since y capital Y L0 and capital Y L1 is a partition of capital XL, where L is in capital I, and capital XL contains exactly one relevant variable in X of capital XL of f. This variable is either in X of capital YL0 or in X of capital YL1, but not in both. Suppose without the loss of generality, it is in X of capital YL0 and not in X of capital YL1. Then f of X subscript capital YL0 concatenation B subscript capital YL1 concatenation V subscript capital X L bar powered by L is a literal, and f of the same thing, but we change the zeros to 1, like it's gonna be L1 and L0 is a constant function. This implies that for any B, f of B subscript capital Y L0 concatenation B subscript capital Y L1 concatenation V subscript capital X L bar powered by L is not equal to f of B subscript capital Y L0 bar concatenation B subscript capital Y L1 concatenation V subscript capital X L bar powered by L. And f of B subscript Y L1 concatenation B capital Y L0 concatenation V subscript capital X L bar powered by L is equal to the same thing basically, but with B subscript Y L1 bar. Therefore, GL0 equals to H and GL1 equals to 0. First, the algorithm does not halt in step 25. Okay. Now for every capital XL, where L is in I, let tau of L in capital XL be such that f of X subscript capital XL concatenation V subscript capital XL bar powered by L in X tau of L and X tau of L bar. If tau of L is in capital Y L0, then G L0 equals to H. And then by step 26, Z tau L is equal to W tau L, which is equal to 0. Okay. So, without the loss of generality, all of these indices on the left, in this example, are the relevant indices. And the relevant variable is in the zeros section. Then it means okay, so this is basically what we said. Okay, if tau of L is in capital Y L1, then capital G L1 equals to H, and then Z tau of L equals to W tau of L bar, which is equal to 0. And therefore, for every relevant variable X tau L in F hat equals to f of X subscript capital X concatenation 0 subscript capital X bar. We have Z tau of L equals to 0, which implies that f of U subscript capital X concatenation 0 subscript capital X bar equals to f of U subscript capital X plus Z subscript capital X concatenation 0 subscript capital X bar, and therefore the algorithm does not halt in step 28. Okay. So we also have lemma 9 over here. If f is k in Junta, then the algorithm outputs accept with probability at least 2/3, and the proof is that the result follows from lemma 6 and lemma 8. Alright, now let's switch to the path where f is epsilon far from every k Junta. In the first part, nothing changes. We create the partition and move to the next part. Here in the second part, in this part we could get a reject as an output in line 10 over here. Then we can assume that this function over here, f, is half epsilon far from k Junta because of lemma 10. Okay, so this is lemma 10. If the algorithm reaches step 13, then t of capital X is equal to 2 ln 15k divided by epsilon, and the size of the relevant groups, which is is less or equal to k if the probability we're using d of f of u subscript capital X concatenation 0 subscript capital X bar not equal to f of u is greater or equal to epsilon divided by 2. Then the algorithm reaches step 13 with probability at most 1 divided by 15. Okay, so let's prove lemma 10. Proof. The algorithm does not reach step 13 if and only if it holds in step 10, and then the size of the relevant groups, the number of relevant groups, sorry, is greater than k. The size of I is increased by 1 each time the condition f of u subscript capital X concatenation 0 subscript capital X bar is not equal to f of u in step 7 is true. Therefore, if the algorithm reaches step 13, then the condition in step 7 was true at most k times, and the size of I is less or equal to k. In steps 8 through 11 are executed at most k times. Thus, t is updated to 0 at most k times. Okay, so the loops 5 through 12 are repeated. The loop is repeated n times, and t is updated to 0 at most k times, and therefore there is capital X for which t of capital X is equal to n divided by k, and that is equal to 2 ln 15k divided by epsilon. And we have this example over here. We perform this test. As we said, this number of times, the most when it don't succeed. And in the worst case, we always find after that many times a relevant variable that we haven't found yet. And we can find up to k relevant variables at most. This implies that when the algorithm reaches step 13, we have t of capital X equal to this number I have said. The probability that the algorithm reaches step 13 with the probability where u is in d of f of u subscript capital X concatenation 0 subscript capital X bar not equal to f of u is greater than epsilon divided by 2 is the probability that for one of them at most k of capital X tag and the probability where u is in d of f u subscript capital X tag concatenation 0 capital X tag bar is not equal to f of u, being greater than epsilon divided by 2, and t of capital X tag is equal to 2 ln 15k divided by epsilon. By the union bound, this probability is less than 1 divided by 15. Because of lemma 10, these will be our probabilities. So we have a success probability of 14 divided by 15 and a failure probability of 1 divided by 15. Okay. Now we can continue to the third part of the algorithm. Here we can assume that our function x projected on capital X, which is x subscript capital X, is half epsilon far from k junta. And after this part, we either output reject or find out something else about the function, which we are going to talk about now in lemma 11. So lemma 11. Consider steps 13 through 15. If for some L in capital I f of x subscript capital XL concatenation V subscript capital XL bar powered by L is 1 divided by 30 far from every literal with respect to the uniform distribution, then with probability at least 13 divided by 15, the algorithm will output reject. Okay, so let's prove lemma 11. If f of what we have said before is 1 divided by 30 far from every literal with respect to the uniform distribution, then it is either case 1, 1 divided by 30 far from every one junta, literal or constant, or case 2, 1 divided by 30 far from every literal and 1 divided by 30 close to 0 junta. In case 1 by lemma 4, with probability at least 14 divided by 15, uniform junta of f of what we have said, 1 divided by 13, 1 divided by 15 is equal to reject, and then the algorithm rejects. Okay, case 2, if the function of what we have said, I'm sorry, this is just too long to read, is 1 divided by 30 close to some 0 junta, then it is either 1 divided by 30 close to 0 or 1 divided by 30 close to 1. Suppose it is 1 divided by 30 close to 1, let B be a random uniform string generated in steps 16, then B is random uniform, and for g of x equals f of x subscript capital X concatenation V subscript capital X L bar powered by L, we have the probability of the algorithm does not reject equals to the probability where g of b is not equal to g of b bar equals to the probability of g of b equals to 1 and g of b bar equals to 0 plus the probability of g of b being equal to 0 and g of b bar equals to 1. All of that is less or equal to the probability of g of b being equal to 1 plus the probability of g of b bar being equal to 1. And that is less or equal to 1 divided by 15. By the union bound, the result follows. Okay. In the end, we will calculate the total probability of the algorithm. But now let's continue to the fourth part. I'll just remind you that we have two loops here, and we want to build this vector z we've said before. Okay, so we have now lemma 12. Consider steps 19 through 26. If for every L in capital I, the function f of x subscript capital X, L concatenation V subscript capital L capital XL bar powered by L is 1 divided by 30 close to a literal in x tau of L bar with respect to the uniform distribution, where tau of L is in capital XL, and GL0 and GL1 are equal to 0 and H accordingly, then with probability at least 1 minus K times 3 divided by 4 times powered by h, we have for every n in capital I, z tau l equals to 0. Okay, so let's prove lemma 12. Okay, so fix some L. Suppose that f of x subscript capital X L concatenation V capital X L bar powered by L is 1 divided by 30 close to x tau of L with respect to the uniform distribution. The case when it is 1 divided by 30 close to x tau of L bar is similar, since capital XL is equal to the union between YL0 and YL1, and YL0 cap, which is the cut between both YL0 and YL1 being the empty set. We have that tau of L is either in YL0 or in YL1, but not both. Suppose the tau of L is in YL0. The case where tau of L is in YL1 is similar, without loss of generality, of course. Okay, so what we do now is define the random variable capital Z of x subscript capital XL equal to 1 if the function on this is not equal to x tau of L and capital Z of that is equal to 0 otherwise. And from that, therefore, E of x subscript capital XL of Z of x subscript capital XL is less or equal to 1 divided by 30. And all of this, where we have a concatenation between xy subscript YL0 and x subscript YL1 is also equal to 1 divided by 30. And by Markov's bound, we get this number. That is for random uniform string B inside all the binary vectors with the length n. With probability at least 3 divided by 4 f of x subscript YL0 concatenation B subscript YL1 concatenation V subscript capital XL bar powered by L is 2 divided by 15 close to x tau of L with respect to the uniform distribution. Now, given that f of x subscript capital YL0 concatenation B capital Y subscript capital YL1 concatenation V subscript capital XL bar powered by L is 2 divided by 15 close to x tau of L. With respect to the uniform distribution, the probability that GL0 is equal to 0 is the probability that the function on the string equal to the function on that thing, but where the B subscript capital YL0 is bar. For each random uniform strings B in all the binary vectors with the length n. Okay, so let B powered by 1 through B powered by H be H random uniform strings in all of the binary vectors with length n. So V of B be the event where the functions are equal, even though over here we have B subscript over here B subscript capital Y and 0 bar, and A the event of the function of X subscript capital Y L0 concatenation B subscript capital Y L1 concatenation V subscript capital XL bar powered by L is 2 divided by 15 close to X star of L with respect to the uniform distribution. Then, probability of V of B, where A is equal to this probability over here, and we keep going with the probabilities and changing the stuff. Sometimes we use the bar, and eventually we reach 4 divided by 15. Okay, since tau of L is in capital Y L0, we have W tau of L being equal to 0. Therefore, by step 26, and since tau of L is in capital XL, and we have all of these probabilities over here, and they are all less or equal to 3 divided by 4 powered by H. And therefore, the probability that Z tau of L equals to 1 for some L in capital I is at most K times 3 divided by 4 powered by H. Okay, so lemma 13. If f is epsilon far from every K junta with respect to D, then the algorithm's output will be rejected at a probability of at least 2/3. Okay, let's prove it. If the algorithm stops in step 10, then we are done. Therefore, we may assume that capital I, like the size of capital I, which is on the number of relevant groups, is less or equal to K. By lemma 10, if the probability will use in D, of course, the function on U subscript capital X concatenation 0 subscript capital X bar not equal to f of U is greater or equal to half epsilon. Then with probability at most 1 divided by 15, the algorithm reaches step 13. So we may assume that failure probability is 1 divided by 15. We assume that the probability of all that stuff not being equal is less or equal to half epsilon. Since f is epsilon far from every K junta with respect to D, and the function on that is epsilon divided by 2 close to f with respect to D, we have that this function is actually half epsilon far from every K junta with respect to D. Therefore, by lemma 5, the probability where U in D and Y in U is a function of U subscript X concatenation 0 subscript X bar equal to F of U subscript capital I concatenation Y subscript capital X without I subscript 0 subscript capital X bar is greater or equal to 1 minus epsilon divided 2. By lemma 11, if sum f of X subscript capital XL concatenation V subscript capital X L bar powered by L is 1 divided by 30 far from any literal with respect to the uniform distribution, then with probability at least 13 divided by 15, the algorithm rejects. So we may assume failure probability of 2 divided by 50. And we may assume that every f on that stuff is 1 divided by 30 close to some x star of L, or some x star of L bar, which is the opposite of it, with respect to the uniform distribution where tau of L is in capital X L. Now let's z through z powered by 1 through z powered by m tag be the strings generated in step 26 by gamma 12 with probability at least of 1 minus n tag k times 3 divided by 4 powered by h is greater than or equal to 14 divided by 15. Every z powered by I generated in step 26 satisfies z tau of L powered by I equals to 0 for all L's in I. Also, since the distribution of W subscript capital XL and W subscript capital XL bar is uniform, the distribution of Z subscript capital X without I powered by I and W capital X without I plus Z subscript capital X without I powered by smaller case I is uniform. We now assume that Z subscript capital I powered by I is 0 for all I, and therefore we go all over through these probabilities until we reach this number, which is less or equal to 1 divided by 50. And therefore, the failure probability of an output reject is at most 1 divided by 15. All of these numbers, we add them together up, and it equals to 1/3. Okay, so in step 2, the failure probability was 1 divided by 15. In step 3, the failure probability was 2 divided by 15, and in the final step, the failure probability was 2 divided by 15, and from lemma 13, the total failure probability was less or equal to 1 divided by 3. Okay. Now let's talk about the query complexity of the algorithm. Now lemma 14. The query complexity of the algorithm is O tilde of k divided by epsilon. Let's prove it, shall we? The condition in step 7 requires 2 queries and is executed capital M, which is equal to 2k ln of 15k divided by epsilon times. This is 2m, which is equal to O of k log k divided by epsilon queries. Step 8 is executed at most k plus 1 times. This is because each time it is executed, the value of capital I is increased by 1, and when capital I is equal to k plus 1, the algorithm rejects. And by lemma number 3, to find new relevant set, the algorithm makes of log r equals to O of log k queries. This is O of k log k queries. Steps 14 and 17 are executed. Less or equal to k times, which is the number of relevant sets. And by lemma 4, the total number of queries made is O of 1 divided by 1/30 log 15k plus 2k, which all of this is equal to O of log O of k. And the final test of the algorithm is repeated n tag times, which is 15 divided by epsilon times in step 18. And each time, and for each L in I, it repeats h times in step 26. 23. Two conditions that takes 2 queries each in step 24. This makes 4 m tag kh equals to O of k divided by epsilon line of k divided by epsilon queries and the number of queries in step 28 is 2m tag of 1 divided by epsilon. Therefore, the number of queries is O of k divided by epsilon line k divided by epsilon. Okay, so let's talk about some open problems that we don't have the solution to yet. Okay, so we saw that in the non-adaptive case we get omega of 2 powered by k divided by 3 queries. And the question is, what is the minimal number of round ones do we need to get poly of k divided by epsilon query complexity? So this is one question. Can all of one round algorithm solve the problem with poly of k divided by epsilon query? Okay, so if we go back to the upper bounds that I have showed in the beginning of this slideshow from previous work, and the lower bounds, which we also have already seen. Therefore, in both cases, the query complexity of Junta testing has now been pinned down to logarithmic factors. We still don't know the query complexity for all of one round algorithms. Okay, so what have we seen today? I explained the model and showed you how the algorithm works. We went through the path for f was k Junta, then we switched to the path for f was epsilon far from k Junta and calculated the total chance of failure. We talked about and proved the query complexity, and then we finished by talking about some open problems. Okay, thank you for watching.